Okay, so hello, welcome everyone. I think we can get started. So today we're going to have another two presentations. This time the focus shifts and we're looking about how computer architecture solutions can also benefit other domains, such as healthcare domains. Here specifically, we're going to target bioinformatics. So let me introduce our first speaker. So Kilian is currently in his second year of his bachelor's degree in computer science. He's very interested in new storage systems and how computer architecture can also be used to accelerate things in natural sciences like biology. So the floor is yours, please.
All right, perfect. Thank you very much for the introduction, and also hi everybody from my side. Yeah, we're going to talk about MARS today. It is a processing in memory acceleration of raw signal genome analysis. So we're going to talk a little bit about biology as well as obviously computer architecture today. MARS is in fact the first in-storage processing design combining processing using DRAM and processing near DRAM within a storage system. So we're going to have a look at this. Let's start. I don't think this control works. Perfect. Yeah, with the executive summary. So what is the problem we are trying to solve? Sequencing throughput gets increasingly more as, for example, sequencer gets improved. And at the same time, certain steps of this pipeline of RSGA gets heavily accelerated by hardware as well as software. And as a result, I/O becomes like the major bottleneck of RSGA. We're going to have a look at this in the motivation phase. So what is the goal of MARS and this paper? First of all, to address this issue of I/O bottleneck, and then leverage ISP, so in storage processing capabilities to accelerate RSGA. MARS itself is the first in storage processing design combining PUM and PNM within a storage system, and MARS is a high-performance, energy-efficient, and scalable system, as we are going to see in the evaluation phase. All right, the results, just a little bit of sneak peek, improves performance by up to 93x, so major performance improvements, and reduces energy consumption by up to 427x. Yeah. All right. As I am the first speaker to speak about genome analysis, I want to give a little bit of a background. Why are we doing genome analysis? Several purposes, including personalized medicine, outbreak tracing, as we have seen in COVID-19 pandemic, as well as research purposes, for example, evolutionary biology. How do we do it? Well, we have this DNA right here. We have like this membrane that separates the negative charge with the positive charge. We have a current flowing through this protein. And we have like a little sequence right here that measures the current. And depending on what base is currently in this protein, so remember the bases, the nucleotide bases of which our DNA consists, adenine, cytosine, thymine, and guanine. And yeah, this is the current the sequencer measures. They are referred to as raw signals. And in a step called base calling, we have this transition where we map these raw signals to the bases. Raw signal genome analysis is what we are going to look at today. And raw signal genome analysis skips this need for base calling. So this step right here. Yeah, so why is RSGA better or maybe more efficient than base calling? Base calling is costly and energy efficient as we have to like add this extra step. RSGA also offers better scalability with portability, and these raw signals give us information that we don't have with only the bases. All right, so let's have a closer look at RSGA and how the pipeline works of RSGA. So in fact, we have two major steps. First of all, we have indexing right here. So this whole step, which is done on a reference genome, so offline before the actual experiment. Right, and the main purpose is to build this hash table. Then we have mapping, which happens online, so in the experiment with an actual genome we want to study. And this separates into 3 major stages, which is first of all event detection right here, seeding right here, and then chaining. And we're gonna have a look at these right now. So first of all, let's focus on event detection. Signal to event. Translate these raw signals up there to events, which are essentially integers. Then we have this step of quantization, which bins these values. So for example, -1 to -0.75 gets mapped to 5, as we see here. And these eliminates the small errors in the input data. So for example, -1.8, minus 0.81 to -0.83, these small errors gets eliminated by quantization. Then let's go over to seeding. So several consecutive events form one hash value. And with this hash value, we query the hash table that got built by the reference genome. And so in this example, we get the hash value of 0x01. We query the hash table and we get these seed hits, all right, which we are gonna focus on in the chaining phase. We sort these seed hits, we chain them together in a order that makes sense. So obviously, if we are currently on position 10 in our genome, and we have a seed hit that is at position 5000. Maybe this is just a coincidence and not really a seed hit that we want to focus on. And we do this in this chaining phase right there. All right, just summarized what I just said. Seeds that are both spatially close and collinear are grouped into anchors. So this is what we see right there. All right, and these anchors then form the basis for every for the constructing for representing high confidence matching regions. All right, let's get to motivation. The motivation for Mars, as I said, is basically the I/O bottleneck that we are facing in RSGA. So we see these are 5 different data sets that differ in size, essentially, mainly. And we see event detection is a bottleneck sometimes, especially in smaller genomes, so D1. Chaining is essentially in every genome a computational overhead. But chaining gets heavily accelerated in a various research projects. So this computational bottleneck gets smaller and smaller, and it gets smaller. Also, I/O bottleneck gets larger. So we see that for every data set that we compare, I/O bottleneck gets over 50% if we heavily accelerate chaining, which happens right now in research. And current works actually overlook this impact of I/O, and this is exactly where Mars is important. All right. Then, this is a motivational experiment. The authors expect I/O to become the major bottleneck, the dominant bottleneck in the end-to-end genome analysis. All right. So what is the goal of the paper? Maybe in 1 sentence, 2 sentences summarized. It is acceleration of RSGA. And why? Also, how are we doing this? We leverage ISP capabilities to accelerate RSGA by using memory and processing near memory paradigm. And we have going to look at this in this Mars section. What is the core idea of Mars? As I said, enable PNM and PUM paradigms within the SSD, so actually within the SSD itself, to create a highly parallel computing system for RSGA inside the storage system. And we do this in two main steps. First of all, software improvements, so filtering techniques, and then specialized hardware. All right, let's focus on the filtering techniques first. First of all, I want to focus on frequency filtering. Frequency filtering is used to identify and eliminate seed hits that cause a large number of seed hits in the reference. So for example, if for any reason, maybe the basis AT occurs again and again, maybe the 5,000th occurrence don't give us that much information anymore, so we filter it out. This is the idea of frequency filtering. Then seed and vote filtering. We group our reference genome into equal sized overlapping windows, and each anchor, so remember anchors where these sorted seed hits, votes for the windows it appears in. And we define two parameters. First of all, the size of the window. So for example, in this case, I don't know, it's probably 10. And then the voting threshold. So every window that gets less than, for example, in this case, 5 votes gets thrown out, because we don't think that it's a likely window in our genome. All right. I want to quickly talk about arithmetic conversion techniques, but I think other presenters have presented that as well. So the basic idea is to reduce bit width from, I don't know, 64, 32 bits to 16 bits. We're going to lose a little bit of accuracy, but we are also reduce storage requirements. All right, let's finally talk about Mars in storage architecture. All right, we first of all partition the RSGA steps that we talked about into fine-grained tasks. Then each task is mapped to a dedicated unit. We have a look at these units in a moment. Mars consists of 5 units: control unit, sorter unit, merger unit, arithmetic unit, and the current unit. The control unit is a finite state machine, kind of like the brain of Mars, if you want to say it that way. And each compute unit is activated only when its inputs are available. So you again see this focus on memory. All right, recall this maybe, because this is going to be important. We focus first of all on the arithmetic unit. We map the operations of event detection to this arithmetic unit. The arithmetic unit implements processing-in-DRAM paradigm. And the control unit, again, is like kind of like the brain. It determines the order of execution for instructions. Yeah, maybe a quick look at the seeding phase. Hash value generation and the filtering happens also in the arithmetic unit. And then the query of the hash table happens inside the query unit, which is this right here. We don't have that much time, so I go over this briefly. The query unit actually implements processing using DRAM paradigm, as you can see here, right? That's our DRAM subarrays. All right. Last but not least, the chaining phase. The sorter unit performs parallel sorting of the seed heads sequences. And the merger unit then again combines these sorted sequences, and both units actually implements processing near DRAM paradigm. All right, let's have a look at how this all works together. So this is actually like the architecture of a usual SSD, with exception of the modified flash controller over there, and then the arithmetic unit that gets added in the DRAM. All right, how Mars works. So we load the raw input signals from the flash memory into the arithmetic unit. We perform event detection there. We generate a hash value and we do the filtering in the arithmetic unit. Then we query the hash table in the querying unit. So as you may see, this is all, there's a specific unit for each task, right? Then we create these batches of sequences that we got from querying the hash table. We load these into the sorter and merger unit, where they get sorted and merged together, and then they are back again in the arithmetic unit, where they are chained together essentially in a process that uses dynamic programming. All right. Any questions so far? Great. All right. Yeah, let's talk about evaluation Mars. So we compare Mars with 5 data sets. So they all differ in size. Obviously, the human genome is kind of the most complex thing to sequence. We compare Mars to these systems. So first of all, we have 2 base calling based pipelines. First is a conventional pipeline, and then GenPip is a hardware accelerated pipeline for base calling. So remember, base calling is essentially RSGA with this extra step of converting the raw signals to the actual bases. We have 3 RSGA based pipelines, RowHash2, which we use as like kind of the main point to compare our systems to. We have Mars executed on a CPU, so that implements the filtering techniques that we talked about. And we have like this pure version of Mars that is hardware accelerated RCA system that we just saw inside the storage subsystem. All right, maybe, yeah, let's briefly go over the hardware setup. We have 2 AMD EPYC CPUs with 64 physical cores. We have a 1 terabyte DDR4 DRAM. And for the SSD, we have 8 channels with each 8 flash chips, PCIe 4.0 interface, and 4 gigabyte LP DDR4 DRAM with 16 banks and 512 subarrays. So first of all, I want to focus on accuracy. So this is RowHash2, which is a state-of-the-art RSGA pipeline, and these are Mars versions executed on a CPU, and that is with fixed point arithmetic, and this is with floating point arithmetic. So first of all, we see that obviously floating point gets a little bit more of accuracy when compared to fixed, because we use more bits, we use more informations, and we see that all Mars systems actually improve in most of the cases the precision and recall of RowHash2. So yeah, maybe a quick info. Precision is essentially of all the mappings we did, how many were correct. The recall value is of all the reads that had a correct matching, how many did we find? And the F1 score is kind of like a combination of both of these. So if the F1 score is higher, it generally means that precision and recall is higher. So we see that the F1 score is actually in every case higher when compared to RowHash2. All right, let's focus on the speed up, the actual performance. Again, we have these systems. So first of all, we see that especially for small genomes, base calling is really slow because you need to add this extra step, and especially for small genomes, just a bottleneck. We see that also Mars executed on a CPU improves performance by on average 1.7x. But we see that this pure version of Mars, so this right here, heavily accelerates smaller genomes, but also on average accelerates by 27.8x, which is of course a major performance improvement. It also outperforms GenPip, which is like the state-of-the-art base calling pipeline. Right. Okay. Then for the evaluation of the energy consumption, I want to add these 2 systems as well, because I think they are quite interesting actually. So this is Mars as we saw it, but with a processing using memory-based arithmetic unit. instead of the processing near memory arithmetic unit that we saw. And this is Mars with a conventional SSD, but then with a ASIC near the CPU to sort things, and a external processing in memory based DRAM. So yeah, let's focus on energy consumption. So again, our basic ground is this raw hash algorithm, which is like the state of the art RSGA pipeline. We see that in every case, actually, all versions of Mars accelerates raw hash 2, which is great. We see that especially in small genomes, the acceleration is very strong. We see that MS-SIM-DRAM actually reduces energy even more when compared to this pure version of Mars or the external version of Mars. And we see that on average, Mars is 180x, 179.4x faster than raw hash 2. Any questions so far? All right, great. Then, yeah, already on the conclusion, some of the highlights of the paper, in my opinion. So Mars is the first in-storage processing system for end-to-end RSGA, including not only hardware acceleration, but also software improvements. It improves performance while also maintaining high accuracy, as we saw in the evaluation phase. And it also highly reduces energy consumption by top of 180x. All right. Yeah, so the strengths of the paper, in my opinion. Mars is the first work to implement in-storage processing design, which was nice to see. I haven't seen it earlier, so it was great to see. And Mars also combines processing using DRAM, processing near DRAM, inside the storage internal DRAM. And it is actually the first design to do so. And I think this design will probably find use cases beyond genome analysis and beyond Mars. So I think this is also a ground for future research projects. The authors also compared a lot of system, including base calling based pipelines with Mars. So I think the evaluation chapter is very thorough and informative, really. And Mars itself achieves speedups up to 84x while also improving accuracy. So of course it was great, yeah, to see how the authors kind of like develop this system that improves RSGA that much. And I also really like that the paper was not only focusing on hardware acceleration, but also on software improvements. So you have like these two grounds. And as we saw, Mars is also faster than raw hash 2 when executed on a CPU. So they are not using the benefits of in-storage processing at all because of these software improvements. All right. Yeah, maybe some weaknesses. The search for the parameters of the filtering techniques are performed offline, so before the experiment. So you cannot really like adjust to, I don't know, maybe noise in the raw signal, for example. And then a second weakness, I think many of the units that we use in Mars are specifically added for Mars to the internal structure of the SSD. And I would like I would have liked to see these possibilities explored further, that you can maybe combine two units. I don't know, maybe combine the sorter unit with the arithmetic unit, but because like obviously every unit you add to the SSD is costly, is maybe energy inefficient. It adds area to the CPU. Yeah, so all right. My discussion, should I just move on or? Yeah, sure.
maybe you can just confirm for me, Mars is actually running in a pipeline, right? So the different stages are running in parallel on different parts of the genome, right?
So the first step, maybe I go back.
So the different parts of the pipeline, like the getting the raw signal, then the merger phase, sort phase, and so on, they're running basically in parallel on different parts of the genome. And once, okay, because then the added CPU has to be quite good at like handling these different things. Once one result becomes ready, to pass it on to the next one. Did you think about what kind of other ASICs or so you could add to the pipeline that are not processing in memory, but add like similar costs to the system to also improve the speed of the system? Because now we have a processing memory system, and that's very good. But the cost that it takes us to build this system, like you've also said with the other chips, maybe we could also build something that's not processing in memory, but achieves even better results or the same results.
Yeah, you basically summarized my second question. So we kind of get to this. And to your first question, actually, so each unit executes when all of its inputs are ready. So essentially, for example, the sorter unit, once the arithmetic unit creates these batches that needs to be sorted, it executes. So yeah.
Maybe I can also clarify something. Because I think the first part of your question was if the compute units inside the storage for all the pipeline are executing in parallel. So they're actually executed sequentially one after another, but within each one, there is indeed parallelism. And because we might have many reads or many raw signals, indeed we can map at the same time at parallel regions of the genome. But the step by step, it's sequential for now, at least. Just to clarify.
Yeah. But this is also a maybe potential for future research, definitely. Yeah. All right. Yeah, my first question is about one of the weaknesses I just mentioned. So for the frequency filtering and the seed and vote filtering, we need these 3 parameters, and the search for these parameters are performed offline. Yeah, my question was kind of like, how can we improve this? So maybe as to recall, frequency filtering is to identify and eliminate the seeds that cause a large number of seed hits in the reference. And also seed and vote filtering. So maybe just to add this, frequency filters uses like a threshold, right? So we need to have a defined threshold after which we throw out every seed hits that occur after this threshold. So this is like the parameter that we use in frequency filtering. We use 2 parameters in seed and vote filtering. First of all, the size of the windows. And second, the voting threshold. So again, how many anchors need to vote for a window so that it stays in the genome. And every window that is below this threshold gets thrown out and excluded from further analysis, because we don't think that it's likely we have like a ground to analyze this. All right. Yeah, maybe your thoughts? Maybe I will give you the first idea I have in mind, which is like a adaptive runtime adjustment. So the system could analyze the first few 1,000 reads, for example, during runtime, and then dynamically readjust the parameters. So what does that give us? If the hardware, for example, detects that the arithmetic unit is overloaded, or the arithmetic units are overloaded, it could, for example, set the filter more aggressively so that more seeds are thrown out, because like maybe you have, we overload the arithmetic unit. The second idea I had in mind was like, kind of like something that we already saw with Pythia in the context of prefetching, like a AI machine learning control, a small lightweight machine learning model in the SSD controller could also monitor signal quality and then adjust the parameters instead of using these fixed values. Yeah.
When trying to determine the quality, the signal quality, do you have to have all 5 steps already executed on some batch, or is it enough to execute the first batch to already evaluate the quality of it?
So, well, you have this reference genome, and essentially the quality is set from 2 passes, precision and recall. So if I understand your question correctly, I think we need to analyze the whole genome, and then we see how many mappings were correct that we did, and how many did we get, how many mappings that were there, how many that did we get from those.
Okay, so we need to execute the whole pipeline once, at least on a small part of the genome, to actually know the quality. Okay, and is the...
Well, we could, for example, the quantization step bins these values. So maybe we can already there check if the bin values are somewhat equal. Yeah, for sure. Yeah.
I think that was an interesting point. And I think basically the answer depends on what kind of control you want to implement. So it could either be some smart way to quickly understand about the quality of the signal in the beginning. So as Kilian said, maybe check if the quantization is enough, if it can be more aggressive or less. But also, if you let the entire pipeline run, maybe you can extract some insights on how the mapping quality is and then do adjustments. But it would be interesting both ways.
All right, then my second question is kind of like about the trade-off between specialization and flexibility. So my first question essentially is, should Mars become more flexible by relying less on specialized hardware? And if yes, how could the Mars architecture be further developed to remain flexible for future algorithms without completely losing the speed advantage of the current architecture? So essentially what I mean is we have seen this transition from base calling to RSGA, a improvement in the general pipeline or the general execution of genome analysis. What if there is a major breakthrough in genome analysis in like a couple of years? Should Mars then maybe we have to throw out every architecture we specifically developed for RSGA? Should it rely less on this specialized hardware, or is this one of the strengths that we should lose because it improves performance that much? Yeah, maybe. And also maybe as a recall, this is the Mars in storage architecture. We see that arithmetic unit and especially the flash controller, so the sorter unit, merger unit, and the control unit are specifically added, as well as other things, to the internal structure of the SSD. Yeah.
I mean, it does depend a bit on how these units are actually implemented. Are they just able to perform these specific operations, or can the merger unit also be used to not only merge like genomes, but also do something in another field of research? And I think especially when we're only thinking about genome analysis, I think there are like some companies that are relying exclusively on genome analysis to develop their products. And for them, I think it would be better or more cost effective to buy the specialized hardware, but to be faster. And as long as there's the need for it or the demand for it, I think it's definitely worth exploring these specialized hardwares. Obviously, if there were a way to make it better without losing this to keep the same accuracy and the same speed without using these super specialized chips. Obviously, that would be better, but as long as there's the demand for it, I don't think it's a bad thing that it is only specialized for it and uses specialized hardware.
Yeah. Thank you. So this is essentially what I also had in mind. I also think like the arithmetic unit, for example, is essentially just an ALU with some registers, so you could use it for other things as well, for sure. Yeah, I thought about this. Maybe instead of fixed sorter units, we could add small FPGA-like structures that could be integrated into the SSD controller. We have seen this kind of in BlueDM, I think it was. Nika talked about this in a paper. BlueDBM, I thought it was like one way you could do this. We could also extend the arithmetic unit to support SIMD operations. We actually did that with this MS SIMD-RAM. We can see actually the improvements for this. We see that the speed up for MS SIMD-RAM is often not that fast than this pure version of Mars, but we see that the area, so the sensitivity to internal DRAM size is roughly the same, and we see that energy reduction is far better with SIMD-RAM, Mars SIMD-RAM, than when compared to this pure version of Mars. And also it's kind of like the best of all these systems. So as you already said, it kind of depends on what do you want? Do you want maximum performance and do not care as much about energy and area? Then go with the pure version. But if you care about energy reductions and area and costs, then it could be a potential for future research projects to maybe explore these possibilities to make Mars maybe a little bit more flexible. All right. I think this is it.
On that note, also, let me add a little bigger perspective in the sense that most of these computational units that are implemented within Mars are actually common computational steps encountered both in base signal analysis, like both in basis and raw signals. So it could potentially indeed be interesting to see how we can leverage these different units to configure new pipelines. And to take it even further, of course, if we could leverage them for completely different domains, that would be a more general purpose thing. Great. Any other questions? Okay, good. Then let's thank our speaker. Thank you for the nice discussion. Okay. So now it's unmuted. You can place it in your pocket maybe.
Thank you.
Okay, so I think we can continue with the second part of today's lecture. The second presentation is going to be conducted by Elena. Elena is in the second year of her master's in electrical engineering. During her bachelor's degree, she has worked on robotics projects, but is now more interested in the direction of computer architecture and embedded systems. She's currently working on a semester project about RowHammer, but her interests are quite broad, as we can see also from her selection. So Elena, go ahead.
Thank you for this introduction and welcome to my paper presentation about Harp, leveraging quasi-sequential characteristics to accelerate sequence-to-graph mapping of long reads. It's a very complicated title, but this paper is actually about genome analysis and how to make it faster. As we've already heard from the previous presentation, genome sequence analysis is critical for many applications. So we can use it to develop personalized medicine, for rapid surveillance of disease outbreaks, as well as understanding genetic variations and learning more about our species and evolution. We do genome sequence analysis with so-called genome sequencing machines, which extract the smaller fragments of the original DNA sequence, and then we have reads in the end. Here, the base calling process that Kilian talked about earlier is already done. But in the end, we want to have a large DNA molecule again. And we do this with a process that is called read mapping. This aligns reads to potential matching locations in the reference genome, which is a human genome that is already known. But this is very, very computationally expensive. So currently the bottleneck. And now to the executive summary. There has been a paradigm shift from sequential reference genomes to graph-based reference genomes. They have all of our variants that appear in the human population and can thus reduce a mapping bias. The problem is now that read mapping is a performance bottleneck, and this has been increased even more due to this paradigm shift to graph-based reference genomes, as graph-based algorithms are a lot more complicated. The goal of the paper is to accelerate the sequence to graph mapping. And the authors did this with a key insight that our genome graphs are quasi-sequential, which means that there are parts that are almost linear and only have very small variance. And with this insight, they were able to reduce the complexity of the graph by quite a lot. So here we have Harp. They built a dedicated data structure called Harp tree, which exploits this quasi-sequential characteristic of the genome graphs, which simplifies graph navigation and also reduces space. In addition, they built a hardware accelerator called HarpX, which significantly speeds up the read mapping process. They achieved an average of a 140 times speed up over state-of-the-art mapping software, as well as a 23 times speed up while reducing chip area compared to the state-of-the-art hardware accelerator. This is our outline, and we're first gonna take a look at the background. So our reference genome. Here we have a linear reference genome, which has been used before, but this leads to a bias in the mapping process due to huge genetic variations in our population. For example, the African genome has around 10% more bases than the current linear human reference genome. So for people from the African continent, lots of information is just missing. For this, we introduce a graph reference genome. This graph-based representation captures the genetic diversity that we have within our population, but because it is a graph instead of just a linear sequence, we now have much more complex computation. Now to read mapping. So we are given a query sequence that we have from our sequencing machine, and we have our reference genome. So now we need to find a path that maximizes an alignment score, which is as similar as possible to each other. So in this example, we have our query read and our reference genome, which would give us this path, but it is not perfect. So we have this one base G that we're skipping, but this is already quite good. So our goal is to find the best path. Read mapping is done with a seed and extend pipeline. So it consists of 3 stages: seeding, filtering, and alignment. And our reference genome is first indexed with small k-length sequences that are unique, that are called k-mers. And we find the locations of these in the reference genome. Then we do our seeding, which identifies short exact matches. So for example, here we have the ACT, which then we can be found on the reference genome, and the other one can also be found on the reference genome. However, and then with this information, we do the alignment. But alignment is very computationally expensive. So first we have a step in between, which is the filtering, which prunes some of the seeds in the reference genome, as there are many false positives and also many repetitive seed hits. So in this case, we would delete our last 2 seed hits and then do the alignment, which determines the exact differences. So we have the A mapping to the A, C, T, C. The G is again missing. And then we have the last 2. Now we're going to take a look at Harp. The key insight from Harp is that 2 human genomes are on average 99.6% identical. This means that a large portion of the human genome graph is sequential. However, there are always some small variations. In most parts, there are only very small variations, and we call these parts quasi-sequences, which you can see here on the left and right side. But in the middle, we have a very, very complex structure that we cannot simplify like this. So the authors looked at these quasi-sequences, and for this, they defined a quasi-sequential criterion. So when a sequence can be looked at as quasi-sequential. And this is when this sequential coefficient is smaller than a defined threshold. This coefficient is calculated with the number of nodes of the graph minus the length of the biggest path. So here we have an example. We have 14 nodes. The longest path in blue is 11. That means our coefficient is 3. With this quasi-sequentiality, they can treat quasi-sequential sequences as linear sequences, and this significantly improves the speed and performance of the read mapping process. Here we have an overview of the Harp architecture. It is an algorithm and hardware co-design for sequence to graph mapping, and which uses this quasi-sequentiality. The 2 most important parts are the Harp tree data structure and the Harp-X alignment algorithm. The Harp tree data structure is a high-level representation of genome graphs. It exposes and uses this quasi-sequential structure. And now instead of saving the entire reference genome graph, which is a few gigabytes, we only save this Harp tree, which is only 1 megabyte. The Harp-X runs this read mapping algorithm consisting of seeding, filtering, and alignment. And it has a special hardware filtering accelerator unit, as well as 8 alignment accelerator units. Now to the detailed implementation of these two components. First, we're going to start with Harp tree, which consists of a table that saves the actual reference genome. It also has lookup tables to speed up the computations, as well as an interface. So our Harp X can communicate with the Harp tree and get the information it needs. The Harp tree is built during the pre-processing stage, and it stores only the nesting hierarchy. So here we have a genome graph, which we can divide into different subgroups. So we have a sequential sequence, which is completely linear. Then we have a quasi-sequential sequence, which is almost linear. But here the parts on the left are also part of a superstructure. So we can't look at them as quasi-sequential. When we build the Harp tree, we can combine sequential and quasi-sequential sequences to a quasi-sequence, and only store that it is quasi-sequence from node 9 to node 63. The superstructure is a bit more complicated, so we need to divide up these two parts and can save them like this. We can use Harp tree, for example, for distance calculation with the help of these lookup tables. Distance calculation is calculated by, for example, here we have the blue point and the green point, and then we first find their common ancestor in red, and then calculate the path, the fastest path from each node to the common ancestor. This can be sped up with Harp tree when looking at sequences, because there we can calculate the distance quite easily as node, for example, node 9, node 16, just 16 minus 9, we know the distance is 7. Now in Harp tree, we do the same thing for quasi-sequences. Of course, this is a simplification, but this speeds up our process. And because our filtering algorithm is error tolerant, we can do the simplification. Another thing Harp tree is used for is sequence alignment. So when we have a region that is fully sequential, we can turn off all of the graph-related components, and this saves up to 40 or 50% of the cycles. Now that was Harp tree, and the next part we're going to look at is Harp X, which implements this read mapping algorithm. The seeding actually is done offline, so in a previous stage, and this accelerator only looks at the filtering and the alignment stages. First, for the filtering algorithm. So here we have a reference and a query, and we have our seed hits. And we want to filter out the seed hits that we don't need. We will take a look at the collinear seed hits. So here you can see S0 and S1, they're close together, so they're collinear, but S2 and S3 are twisted. So we're not going to look at them. Then we will merge the collinear ones into a chain. And then from these chains, we select the alignment candidates with the highest scores to then have our alignments that we will use in the next step. This is done with a one-dimensional dynamic programming algorithm that has been also used in other papers. But the difference here now is that it uses the distance calculation from Harp tree. The accelerator itself looks like this. So in blue is the algorithm implemented, and it communicates with the interface of the Harp tree. To ensure that we don't have memory congestion, they use fine-grained pipelining. This blue array has a filtering sensitivity of 97%, which is already quite good in my opinion. But the authors decided to add a second auxiliary array, which adds a sensitivity gain of 0.4%. It doesn't use the Harp tree interface. It just looks at everything as if it were a sequence. So it is not perfect, but it is quite fast and area and energy efficient. So they decided to implement this for the sensitivity gain. Now for our alignment algorithm. We do our alignment with the DP version of the Smith-Waterman algorithm, which can be seen here, but this is a two-dimensional version. But here, there are some data dependencies, which are the neighboring tiles. As we have genome graphs, the authors decided to implement a tile-based heuristic, which uses different tiles that map over each other. But this also gives us a bit of a problem, as there are boundary crossing long hop edges. So here you can see two tiles, and in between there is a long hop edge, which is too far away. So the solution is just to build a new tile. The alignment accelerator itself consists of a top-level module, which splits the alignment tasks into multiple tiles, and then a tile-level module, which performs the sequence to graph alignment within a tile. It has traceback memory banks, as well as a compute engine with alignment elements. As the data dependencies are a bit more complicated in genome graphs, the authors added these max registers. The data dependencies depend on runtime information, so they cannot compute them offline. But these max registers keep track of the cell updates and are also quite fast, which makes them very useful. This was the overview of the implementation with Harp tree and HarpX implementing the read mapping algorithm. Now to the results. First, the methodology. So to compare their performance, they used a dual approach. First, they have an RTL simulation, which is quite accurate, but they only use it on small data sets, as it is also complicated and a bit time-consuming. For larger data sets, they used a software simulation and had two separate simulators for the filtering and the alignment stage. The baselines they used, for software, they used Graph Aligner and Minigraph, and for the hardware accelerator comparison, they used Segram. They had 6 reads with different error profiles ranging from 0.5% errors to 10%. And now you can see an overview of the performance evaluation. So you can see here that on average, they have 140 times speed up compared to Graph Aligner, almost 80% speed up to Minigraph, and 23 times speed up to Segram, which is the hardware accelerator. Compared to Segram, they also were able to achieve a chip reduction, reduction of the chip area of 73%. And they mentioned that this is mainly due to the improvements in their filtering technique. You can see for the low error rate reads, so this one and this one, the comparison with Segram is missing. This was because they didn't have these data sets available when they published their paper. But you can also see that Harp has quite a good performance, so even better with low error rate reads, as their filtering is more accurate then. Now let's take a look at our accuracy. So this compares the precision to the sensitivity. And you can clearly see that you have better accuracy, but this also leads to some performance issues. So the authors decided to use their their DP values, they set them empirically to achieve a sensitivity of around 98%. And you can see here the comparison with, so n is the number of filtering elements that they used. For low error rate data sets, they achieved an even higher sensitivity of 99% and less false positive, so less than 2%. Now to the speed up, they used the graph aligner software baseline without filtering as a base. And already with just adding filtering, there's a speed up of 257 times. Adding the optimization with Harp tree gives, again, quite a bit of a speed up. But this is all in software, so with no hardware accelerations. Adding the alignment hardware acceleration gives, again, a speed up of 3.6, and adding filtering acceleration and speed up of 27.1. Filtering and alignment then optimized with Harp tree gives, again, a speed up of 1.2x. So these were the results, and now to the conclusion. We had this paradigm shift from linear reference genomes to graph-based reference genomes, which makes our read mapping process a lot more complicated and reduces performance. So the goal was to accelerate the sequence to graph mapping, which they achieved with their key insight of quasi-sequentiality. They developed Harp tree, a dedicated data structure exploiting the quasi-sequential characteristic, as well as HarpX, the hardware accelerator. They achieved 140 times speed up over the mapping software, as well as a 23 times higher throughput over the current hardware accelerator. Are there any questions? Okay, then I'm going to continue with the strengths and weaknesses. So what I really liked about this paper is that it addresses quite a relevant problem. As we have already heard, genome sequence analysis can be used in a wide range of topics and can lead to many benefits for us as a population. And also these genome graphs, which help reduce mapping biases, I think it's also quite important that we study them and are able to have improvements in this direction. I also really like their algorithmic innovation, that they were able to identify that these genome graphs are most of the time almost sequential, and were able to achieve quite some speed up with this. Another point that I liked was their algorithm and hardware co-design. So they designed these two specifically hardware-based components, which leverage quasi-sequentiality, but also were specifically designed to make this read mapping algorithm faster. And this led to very good results. So 140 times speed up and a 23 times higher throughput, I think is quite remarkable. And also reduction of the chip area. Their weaknesses, I think quasi-sequentiality is quite an interesting topic, but it might be a bit limited with more complex graphs, so performance may degrade if we have less quasi-sequential regions. So we know this is the case for our human genome, but what about other non-human genomes? Maybe there are bigger variations there, so they didn't explore any of this, or what would happen if we had a much more complex graph. I also think they didn't fully explore their optimization potential. So maybe they could have used a bit more aggressive filtering to improve results, as they just set the values for their filtering empirically. And also for Harp tree, they could have used Harp tree for sequence alignment as well, and maybe also made this a bit more aggressive. But of course, this also depends on how much error you are ready to have. Something I thought was a bit difficult was their explanation of the alignment algorithm. So this core approach was quite difficult to understand. And also I couldn't find anything of their stuff open source. So this prevents anyone from trying to improve this or trying to learn from this and maybe use their insights and their code, and you don't have to start from scratch if you want to use quasi-sequentiality for genome sequence analysis. Also, everything they did was based on long reads, and they didn't test anything using short reads. And now to the discussion. First, I want to present a new idea that I had. So I thought maybe we could combine the strengths of these two hardware accelerators, Harp and Segram. If you remember, Segram had a speed up of 20, so Harp had a speed up of 23 times over Segram, which is mainly due to their filtering technique. But we could maybe use Harp tree to speed up the filtering, as well as use the alignment accelerator from Segram. They used a bit vector-based alignment accelerator, which can exploit bit parallelism and was quite fast in that way. And maybe combining this with the filtering from Harp tree could lead to even better results. Anyone else have any new ideas?
So those quasi-sequential graphs, if you were to construct an adjacency matrix representation of the quasi-sequential graph, it would actually become a sparse matrix because most of the nodes are just connected to one single node. And there is a very well explored literature as well as hardware acceleration techniques to accelerate graph-based algorithms on sparse graphs. So do you think something like Bellman-Ford or Floyd-Warshall, so these are the algorithms that give you the shortest distance between all of the nodes. So these are like essentially single scan algorithms, and they give you the shortest distance in just one go if you make it run until it stabilizes. Do you think maybe that could be done to estimate the distance in a similar way as to how they have done, especially for the quasi part, like especially subtracting the linear part? Maybe all of that innovation is already there in the sparse matrix literature.
Yeah, that's a very good point. I didn't think of that, but I think that sounds like a very good possibility to have something different than the quasi-sequentiality with these sparse matrices. Yeah, sure, this could be a direction that could be explored. And yes, then to our discussion part. So we have this reference genome, which is quite complicated, but maybe even before starting our entire read mapping process, we could further improve it. So do you have maybe some ideas on how to do that? So one thing I thought of was that depending on personal information about the person whose DNA you're trying to map, for example, ethnicity or also hereditary dispositions, you could reduce the complexity of the reference genome. And so if you know for sure some variants are not going to be present in this person, then maybe you could reduce the very, very complex parts that we have here in the middle to only smaller variants. And then we have an even bigger quasi-sequence, which could lead to, again, more improvement. Yes?
Does this only apply to the things that we are sure they're not in the genome, or also the parts of the genome that we're maybe just not interested in? Can we just like skip parts of the genome?
Yeah, I think both could work. So maybe if we, if we know that we're only interested in a certain part of the genome, that we can just cut the reference genome in half and only look at this. I think that's also a very good idea.
It may help to have more of the genome, especially when we're looking at the non-quasi-sequential regions. If we try to map, for example, the beginning of the non-quasi-sequential region, so the complex region, it may help if we have some overlap between the quasi-sequential region, because the end of that one might be very trivial to match. And then we can get like the beginning of the non-quasi-sequential region pretty easily, if you understand what I mean. So we should try not to reduce the complexity too much, especially trying to, I think it's good to try to keep as many quasi-sequential regions as we can to have this easy mapping and to try to filter out like errors that we could have if we try to match only partial regions and then we match a wrong region just because we reduce it too much.
Yeah, that of course could also be an issue if we delete too many of the variants. We of course run into the same problem again that we have if we just use a linear reference genome. So there's a trade-off that we have to make on how exact we know, and maybe also only reduce that if we're sure that based on where this person is from, these variants really will not be in their DNA. As a next point, I have quasi-sequentiality in other domains. So which other domains could quasi-sequentiality be applicable to? We have a reference genome where we know almost everything is sequential and there are only small branches. Could you think of another part where this happens? So my ideas were that it could be used maybe for logic and circuit design, where we have control flow graphs. These are usually long sequences of operation across multiple timeframes, and then sometimes we have some branches. But all in all, it is a long path through time. Maybe quasi-sequentiality could lead to a bit more efficient graph traversal and reduction, as we only have a few branches and maybe some parts that don't have any branches at all. And there we could again look at this in a sequential way. Another option would be version control, maybe Git, or also checkpointing in persistent memory, where we save the current state of a running application to a storage medium. And this is mostly sequential logging. But some parts are non-sequential, but then we could treat everything. So where there's only small variances, we could treat it as sequential and then only do our more complex calculations on the rest. Now, I think a very important question that I was asking myself all the time is how much error can be tolerated? I don't really have an answer to that, but I wanted to go over the quasi-sequentiality again. So they looked at this sequential coefficient, which is the nodes minus the longest path. So in this case, 3. But I am wondering, how do you find the perfect cutoff from where a sequence is still quasi-sequential and where some part can only are too complex and have to be looked at as a graph? So what they did is they just did empirical testing, looked at different coefficients, looked at how much error they had, and then decided that they would go for a coefficient of 6. Yeah, I'm sure this also depends on the application. do you have any additional ideas on how we could find this trade-off?
Should this coefficient not also be dependent on the size of the graph? So currently we're only subtracting the number of nodes that are not actually in the longest path, but maybe like a value from 0 to 1, so just dividing by the size of the graph would already give us a better approximation for all kinds of sizes of graphs and not only for small graphs.
Yeah, that's a good point. So we could also use a different coefficient even. Yeah, I think for that we would also maybe have to do empirical testing and check how much error we have with which cutoff. But yeah, for longer sequences, that sounds like a good idea. Then we had the quasi-sequential criterion cutoff, but also Harp tree may cause inaccuracies, but the filtering algorithm is error tolerant. So they set the values for their DP, they set empirically and achieved this precision. I was also wondering if this could be improved, but of course, this depends on how much error can be tolerated, also depending on different applications. Another thing I also thought of was that if an alignment region is fully sequential, they disable all graph-related data components. But to make sure that this is correct for sure, they only do this if the sequence is fully sequential. Maybe you could also use either a different criterion completely, or also a different cutoff. So maybe for the alignment part, we could use a cutoff that is 1 or 2 instead of 6, because we want less error there. And this might already drastically improve our computation as half of the cycles are saved. Yes.
Would it, in your opinion, be worth it to explore whether we should separate into quasi-sequential and actually sequential regions? So even if we have like only 2 nodes that may be skipped in some parts, this is currently treated as a quasi-sequential region. Could we split it into then 3 different regions that are fully sequential, fully sequential, fully sequential, and just the part in the middle, which is partially sequential? Would that be also something worthy of doing, or would that be too complex?
I think the problem with this approach is that it would make one of our advantages of Harp trees so that it significantly reduces the size. Yeah, we'll go back a bit. But otherwise, if you want a very exact sequence, I think this could also be a good idea. Yeah. And then as our last point, I wanted to mention the co-design of the software and hardware part. So they have a hardware accelerator, which has very significant speed up. So you can see the first part is only software. And then using hardware again, we have, again, a huge speed up as we can exploit a high level of parallelism. But we also here, we have an energy versus cost trade-off. So as Kilian already mentioned before as well, dedicated hardware is very expensive to develop. So we have this non-recurring engineering cost. And we can, but when we have this, so when we have our dedicated hardware, we significantly reduce the cost per alignment and also the energy consumption. So now, is there another way to reduce this engineering cost so that it is so expensive to develop? So a possibility is to increase flexibility. And there is a paper on this called GenDP, where they built a dynamic programming accelerator framework. And as you might remember, filtering as well as alignment uses dynamic programming algorithms. So maybe you can use this framework and then you have some additional ideas on how to speed it up even more, and you can implement them on top of this. This would then reduce the engineering cost very much as the framework is already built completely. Yeah, thank you for listening to my talk about the paper Harp. And do you have any additional questions?
Okay, then. Thank you very much, Elena. So I think then we're done for today. Don't forget to fill in the quiz and feedback to presenters and your mentors. Okay, see you next week.